Hello. In this video, I'm going to walk you through the Getting Started notebook for the BleakHeart package. BleakHeart is an open-source asynchronous driver for heart rate monitors that implement the standard Bluetooth Low Energy Heart Rate Service specification. It also supports the Polar Measurement Data Protocol that allows it to read ECG and accelerometer signals from the Polar H10 and compatible wearables. You will find this notebook, the BleakHeart source code and other examples in the GitHub repository linked in the description. To run this notebook, you need to have BleakHeart installed in your Python environment. You can install it by uncommenting and running the code in this cell. This will also install the Bleak library that provides Bluetooth Low Energy connectivity. Next, we import the two main Bleak objects, as well as Async IO and the BleakHeart package itself. As a first step, let us connect to the device. For this to work, you need to make sure you're wearing your heart rate monitor correctly and that the BLE adapter on your computer is enabled. This code searches for a device by its advertised name, creates a client object and establishes the connection. The client object is our handle to the device. As you can see, I am wearing a Polar H10. If you have a compatible device from another manufacturer, you can edit the string accordingly. For a detailed explanation of ways to detect and connect to your device, refer to the Bleak documentation. As our first exercise with BleakHeart, let's look at how to read the battery level of the device. For this purpose, we just need to create a battery level object by passing the client object to its constructor. We then call the read method that returns the battery level as a percentage. Notice that read is an asynchronous method and therefore must be awaited. Since the JobHeader server runs its own asynchronous event loop, we do not need to worry about creating and managing the loop and can simply use the await keyword. The battery level object should work with any device that supports the standard BLE battery service. Next, let's see how we can read the heart rate and RR intervals, also called beat-to-beat intervals. According to the heart rate service specification, devices transmit packets including the average heart rate and, if supported, a list of RR intervals and an estimate of energy expenditure. BleakHeart decodes such packets as Python tuples, adding the HR tag to the front and the system timestamp in nanoseconds for the time the packet was received. The number of RR values included in each packet is controlled by the sender and can vary from packet to packet. For convenience, BleakHeart can unpack such data into a sequence of tuples, each containing a single RR value. In this case, an option is provided to replace the average heart rate with an instant heart rate computed from each RR interval. The heart rate can be acquired using the heart rate object. This object can return data in two ways, via a callback function or via an asynchronous queue. In this example, we use the JobHeader function as the callback. In this way, packets will be displayed in the notebook as they are received. For this example, we set instant rate to true and unpack to true. The code in this cell controls the actual acquisition. Awaiting the start notify method starts heart rate notifications on the device. The sensor will then stream heart rate packets until the stop notify method is called 5 seconds later. As we can see, the packets conform to the format described above. The Polar H10 supports RR intervals, but it does not support energy expenditure, hence this value is always none. Note that the callback function is a blocking operation, and therefore it should return promptly for BleakHeart and the other asynchronous functions in Bleak to keep on receiving and processing data. A second, more flexible asynchronous workflow for the heart rate object involves a producer-consumer model. In this scheme, BleakHeart, the producer task, is configured to write packets to an asynchronous queue that acts as a buffer. The queue is consumed by an asynchronous consumer task that reads the data and processes them. In the following cells, we will introduce and test the producer and consumer tasks one at a time before running them concurrently. First, let's create the asynchronous queue. This coroutine is the producer task. In it, we create a heart rate object and pass to it the asynchronous queue in place of a callback. We then start notifications on the device and wait for 5 seconds before stopping them again. Finally, we put a special token on the queue. This will be used as a signal for the consumer task to exit. Let's run this cell and await the producer task. As can be seen, a certain number of packets is put on the queue. This other cell defines the consumer task coroutine. This consists of an infinite while loop. In it, we just wait for a data frame to be available on the queue. We then signal to the queue that the item has been processed and print the data. The loop is exited when we encounter the end token. We now have a few tuples on the queue from running the producer task above, so awaiting the consumer task will simply print them. Most of the time, in actual usage, we would want the producer and consumer tasks to run concurrently. This can be achieved very simply by using gather, as shown in this cell. The while loop is there to ensure that the queue is empty before the two tasks are started. As we see, the two tasks run concurrently, and packets are retrieved and printed continuously as they are put on the queue. On top of the standard services, Polar sensors implement the Polar Measurement Data API that allows accessing additional measurements such as ECG or accelerometer data according to the specific device. BleakHeart supports access to these measurements via the Polar Measurement Data class. As a first step, creating a Polar Measurement Data object and awaiting the available measurements method returns a list of the measurements supported by the device. In the case of the Polar H10, these are the ECG and accelerometer data. The available settings method can then be used to determine the possible settings for a specific measurement. These are returned as a dictionary with the settings as keys and the possible values as lists associated to the keys. In our case, the only settings available for the ECG are a sampling rate of 130 Hz and 14-bit precision. Polar Measurement Data supports both the callback workflow and the consumer-producer model, as seen above. Here we will push the frames to an asynchronous queue. To do that, we instantiate the queue and pass it to the constructor of the Polar Measurement Data object. Data acquisition is started by awaiting the start streaming method with the desired measurement as its argument. The while loop in this code keeps waiting in 1-second intervals until at least 10 ECG frames have been added to the queue. The number of samples in a frame is not specified, but in practice, 10 frames correspond to about 5 seconds of ECG signal, though initialization will take a bit longer. The queue size method allows us to obtain the size of the queue. getNoIc can be used to retrieve an item from the queue and, for instance, print it. As can be seen, packets are formatted as tuples consisting of the ECG tag, followed by the centered timestamp of the last sample in nanoseconds and by a list of samples in microvolt. We can now use matplotlib to display the ECG signal. Matplotlib is not a dependency of BleakHeart. You can, however, install it if needed by uncommenting the first part of this cell according to your Python package manager. This plotting code simply concatenates a list of samples from all packets in a queue. Samples are then divided by 1000 to convert them to millivolt. A timescale is created based on a sampling frequency of 130 Hz, and the ECG signal is then plotted against it. As we have seen, beside ECG data, the Polar H10 can stream acceleration data. This time, a call to available setting shows a range of different options for the sampling rate and measurement range. The defaults set by BleakHeart can be accessed via the default settings attribute of Polar Measurement Data. These settings can be overridden in the call to start streaming. Using these defaults, we again declare an asynchronous queue onto which the accelerometer readings will be pushed. We pass the queue to the constructor of Polar Measurement Data. Once again, streaming is started by awaiting start streaming and stopped by awaiting stop streaming. The while loop keeps sleeping until 20 packets have been received, which should happen in around 5 seconds. We can use queueSize to check for the actual number of packets received. As can be seen, frames are decoded as tuples starting with the ACC tag, followed by the center timestamp of the last sample in nanosecond and by the list of samples. Each sample is a tuple containing the 3-dimensional acceleration vector recorded in units of 1,000th of the standard acceleration of gravity g. Again, using matplotlib, we can consume the queue and plot the data. Here we have to divide by the sampling rate when building the timescale. Likewise, if we would like the y-axis to be in units of g, we need to divide each acceleration channel by 1000. As a final example, let's have a look at ways to acquire 2 types of measurements simultaneously. The key thing to remember is that we should only allocate one instance of Polar Measurement Data for each device. This single instance will allow us to stream both accelerometer and ECG data. Of course, if we wanted to stream also the heart rate at the same time, we would also need a separate heart rate object. In this case, we create 2 separate queues for the 2 types of measurements and pass them to Polar Measurement Data. We then await the start streaming method for each of the measurements. At the end of the 8-second window, we await stop streaming on the 2 types of data. Note that the 2 types of frames are not transmitted at the same rate, so the 2 queues will likely contain a different number of frames. Having 2 separate queues allows us to process the 2 types of measurements asynchronously as they are received. If we instead want to process all frames in the order in which they are received, a convenient way is to use a single queue for both measurements. Alternatively, we can send all data to a callback, as in this last example. Either way, we can use the tag embedded as the first element in each data tuple to tell apart packets containing different measurements. In this example, we again await start streaming for each measurement type. As we demonstrate here, there is no requirement that stop streaming be called at the same time for both measurements. This concludes our introduction. You can use the help function on BleakHeart classes for more information. Thanks for watching, and many happy lines of coding with Apache Python.